There's something haunting about the quietest corners of the universe. Picture this: a vast, endless expanse where sound doesn't travel, where light stretches thin, and where the very fabric of space seems to hold its breath. It's easy to assume these silent voids are empty, meaningless, just cosmic deserts between the stars. But what if I told you that these quiet regions are actually the universe's most profound storytellers, that within their stillness lies the key to understanding everything from the birth of galaxies to the invisible forces shaping reality itself? Think about the last time you sat in complete silence. Maybe it felt unsettling, even eerie, but silence isn't just the absence of noise, it's a canvas. And the universe paints its grandest mysteries across that canvas in ways we're only beginning to decipher. Take dark matter, for example. It doesn't glow, it doesn't cast shadows, and yet it makes up most of the matter in the cosmos. Or consider the cosmic microwave background radiation, the faint afterglow of the Big Bang, whispering secrets about the infancy of everything we know. These aren't just scientific curiosities, they're clues hidden in plain sight, waiting in the quietest places for us to listen. So why do these silent stretches of space hold so many answers? Because they're the universe's way of stripping away distractions, leaving only the raw, unfiltered truth behind. When we tune out the noise of stars exploding and galaxies colliding, we start to hear the deeper rhythms, the hum of quantum fields, the echoes of ancient events, the invisible threads weaving reality together. This isn't just astronomy, it's a detective story on the grandest scale. And by the end of this journey, you'll never look at the empty night sky the same way again. The universe's quietest corners aren't voids, they're treasure chests, and we're just beginning to unlock them. It's almost poetic, the idea that the emptiest places in the cosmos are hiding the universe's biggest secrets. Think of it like standing in the middle of a desert at night. At first, all you notice is the vast nothingness, but then your eyes adjust, and suddenly you see stars so vivid they feel close enough to touch. That's exactly what's happening in these cosmic voids. What looks like emptiness is actually a frontier of discovery, where the absence of light and sound lets us observe phenomena that would otherwise be drowned out by the universe's chaos. Take dark energy, for instance. This mysterious force is causing the universe to expand faster and faster, yet we've never seen it directly. So where do scientists go to study it? Not the crowded galactic centers or the fiery hearts of stars, but the quietest, most uneventful patches of space. It's there, in the stillness between galaxies, where the subtle effects of dark energy reveal themselves. Without the distraction of nearby stars or swirling dust clouds, researchers can measure how the fabric of space-time itself stretches over time. Then there's quantum fluctuations, tiny ripples in reality that pop in and out of existence everywhere all the time. Normally, they're too faint to detect, but in the near-perfect silence of cosmic voids, these fleeting disturbances become detectable. It's like trying to hear a whisper in a crowded room versus an empty auditorium. The quieter the space, the clearer the signal. Some scientists even believe these quantum whispers could hold clues about the birth of the universe or the nature of gravity itself. And that's the real magic of these silent stretches. They strip away the noise, leaving only the universe's rawest, most fundamental processes on display. It's as if the cosmos is handing us a magnifying glass, saying, "Look closer, the answers were here all along." So while the voids may seem like the universe's forgotten corners, they're actually its most revealing classrooms. The silence isn't empty, it's alive with possibility. dark matter is like the universe's silent architect building structures we can't see but whose handiwork is everywhere. Imagine a skyscraper with invisible scaffolding, holding everything together while remaining completely hidden. That's dark matter. It doesn't emit light, reflect it, or interact with ordinary matter in any way except through gravity. Yet without it, galaxies would fly apart, and the cosmos as we know it wouldn't exist. Now, here's the fascinating part. The emptier a region of space appears, the more dark matter dominates. In crowded galactic neighborhoods, stars and gas clouds steal the spotlight. But venture into the quiet voids between galaxies, and suddenly, dark matter's gravitational fingerprint becomes undeniable. It's like turning down the volume on a noisy room until you hear the faint hum of a hidden machine. One of the most striking proofs of this comes from something called the bullet cluster, a cosmic collision where two galaxy clusters slammed into each other. The visible gas clouds crashed and slowed down, but something kept hurtling forward, bending light in a way that revealed an invisible mass. That something was dark matter, parting ways with ordinary matter like a ghost slipping through walls. These quiet cosmic regions aren't just empty space, they're pristine laboratories. Without the interference of bright stars or swirling dust, scientists can map dark matter's distribution by studying how it warps the light of distant galaxies, a phenomenon called gravitational lensing. It's like reading the universe's hidden blueprint by watching how light bends around unseen structures. Some theories suggest dark matter could be made of exotic particles that barely interact with anything, which is why it's so hard to detect directly. But in the silence of cosmic voids, even the faintest signals stand out. What's truly mind-blowing is how much we still don't know. Dark matter isn't just some minor cosmic ingredient. It makes up about 85% of all matter in the universe. That means everything we can see, from planets to stars to galaxies, is just the tip of the iceberg. The rest is an invisible framework, sculpting the cosmos on scales we're only beginning to comprehend. And the quieter the space, the clearer the message. The universe is far stranger, far richer than what meets the eye. If you want to hear the universe's oldest story, you have to listen to its quietest hum. The cosmic microwave background is like a fossilized whisper from the moment everything began, a faint glow of radiation that's been traveling for over 13 billion years, carrying secrets from the universe's first breath. Picture it as the afterimage of the Big Bang itself, stretched and cooled by the expansion of space until it became a nearly imperceptible microwave signal permeating every corner of the cosmos. What makes this ancient light so extraordinary isn't just its age, but what it reveals. Embedded in its subtle fluctuations are patterns, tiny variations in temperature no larger than 100,000th of a degree. These aren't random imperfections. They're cosmic fingerprints, evidence of density, ripples in the early universe that eventually grew into galaxies, clusters, and the vast web of structure we see today. It's as if we've uncovered the universe's blueprint, hidden in the static of empty space. But here's the catch: you can't study this signal in the bustling heart of a galaxy. The cosmic microwave background is so delicate that even the glow of interstellar dust or the shimmer of distant stars can drown it out. That's why scientists seek the emptiest regions of space, where interference fades to near silence. In these voids, the CMB shines through with unmatched clarity, like a single candle in a pitch-black room. Some of the biggest breakthroughs in cosmology have come from this quiet scrutiny. The CMB has confirmed the universe's flat geometry, hinted at the existence of dark energy, and even provided clues about cosmic inflation, the explosive expansion thought to have occurred in the first fraction of a second after the Big Bang. Each new observation peels back another layer, revealing how the infant universe behaved under conditions we can't replicate in any lab, and the most humbling part. This ancient light is still talking. Every time we improve our instruments like the James Webb Space Telescope or next-generation ground observatories, we hear more of its story. The cosmic microwave background isn't just a relic. It's a living archive, patiently waiting in the quietest corners of space for us to learn how to listen. The deepest cosmic voids might seem like perfect emptiness, a pure, unbroken silence stretching across light years. But here's the twist: even in these desolate expanses, the universe is never truly still. Beneath the surface of what we perceive as nothingness, space itself is a bubbling cauldron of activity, thanks to something called quantum fluctuations. Imagine the void as a calm lake at night. From a distance, it looks perfectly smooth, but peer closer, and you'll see tiny ripples appearing and vanishing in an endless dance. That's the quantum vacuum, a place where particles and antiparticles flicker into existence for the briefest moments before annihilating each other, leaving no trace behind. These aren't just theoretical quirks. We've actually observed their effects in labs through experiments like the Casimir effect. Take two uncharged metal plates and place them incredibly close together in a vacuum. Classical physics would say nothing should happen, but in reality, the plates get pushed together by an invisible force. Why? Because the space between them is too narrow for certain quantum fluctuations to fit, while the space outside remains chaotic. The result: the plates experience pressure from the quiet of the quantum foam itself. It's as if the universe is whispering, "What you call empty is anything but." What's even wilder is that these fleeting particles might hold the key to one of physics' greatest mysteries, uniting gravity with quantum mechanics. Einstein's theory of general relativity describes the cosmos on a grand scale, while quantum mechanics rules the subatomic world, but the two don't play nicely together. Quantum fluctuations, though, exist at the intersection of both realms. In the utter silence of cosmic voids, where gravity's grip is weakest, these tiny ripples could reveal how space-time behaves at the smallest scales. Some theories suggest that if we could measure these fluctuations precisely enough, we might even detect the faint imprint of gravity's quantum nature, a breakthrough that could rewrite our understanding of reality. So when we talk about the universe's quietest places, we're not talking about true emptiness. We're talking about a stage where the most fundamental processes play out unseen. The quieter the environment, the louder these quantum whispers become. And that's the beautiful paradox. The more we tune out the noise of stars and galaxies, the more we hear the universe's deepest hum, thrumming just beneath the surface of silence. Between the glittering islands of galaxies, there's an ocean we barely see, an immense, ghostly sea of gas so thin it defies belief. This is the intergalactic medium, a diffuse fog of matter that stretches across millions of light years, invisible to the naked eye, yet holding more ordinary matter than all the stars and galaxies combined. If you could scoop up a handful of this space, it would feel emptier than the best vacuum we've ever created on Earth. But don't let its faintness fool you. This is where the universe hides its raw materials, the primordial hydrogen and helium left over from the Big Bang, waiting to be pulled into galaxies or blown out by cosmic winds. To study this hidden reservoir, astronomers turn to nature's flashlights, quasars. These ultra-bright cores of distant galaxies beam light across the cosmos, and as that light passes through the IGM, it carries fingerprints of the gas it encounters. Think of it like sunlight filtering through stained glass, where each color absorbed tells a story about the glass itself. By analyzing the subtle dips in a quasar's spectrum, called absorption lines, scientists can map the IGM structure in astonishing detail. Some of these lines reveal vast filaments of gas, the cosmic scaffolding along which galaxies form. Others betray ancient bubbles blown by exploding stars, or the turbulent wakes left by colliding galaxy clusters. What's truly remarkable is how these quiet regions preserve the universe's history like pages in a book. The IGM hasn't been stirred up by star formation or shredded by black holes, so its composition remains largely unchanged since the early cosmos. In its whispers, we find echoes of the universe's adolescence, clues about how the first galaxies ignited, how matter clumped together, even how the cosmic web took shape. Without the noise of nearby stars, these faint signals stand out with startling clarity. And here's the kicker: the IGM isn't just a relic, it's still shaping galaxies today. When a star explodes or a black hole erupts, it can fling matter back into this intergalactic sea, where it might someday be recycled into new stars. It's a cosmic conveyor belt, with the IGM as both the starting point and the graveyard for the stuff of galaxies. So while these voids might seem like the universe's backwaters, they're actually its lifeblood, silent, unseen, but utterly essential to everything we know. There's a strange irony at the heart of black holes. The most chaotic, destructive forces in the universe are also surrounded by perfect silence. Picture the event horizon, that invisible boundary where gravity becomes so strong not even light can escape. From the outside, it looks like a shadow, a dark circle framed by the glowing disk of superheated gas spiraling into oblivion. But that shadow isn't just an absence of light. It's a portal to understanding gravity pushed to its absolute limit. Projects like the Event Horizon Telescope have given us the first glimpses of these eerie silhouettes, like the iconic image of the black hole at the center of galaxy M87. That fuzzy orange ring, that's light bending around the event horizon, a cosmic mirage created by space-time itself, warping like a funhouse mirror, but the darkness at its core. That's the shadow, a region where gravity wins, swallowing everything, even the laws of physics as we know them. What's fascinating is how much these silent shadows reveal. By measuring their size and shape, scientists can deduce a black hole's mass, spin, and even test whether Einstein's theory of relativity holds up under such extreme conditions. It's like studying a tornado by the stillness at its center. The quieter the shadow, the louder it speaks about the forces shaping it. And here's the mind-bending part: that silence isn't passive. The event horizon hums with quantum activity, virtual particles popping in and out of existence in ways that might slowly leak energy, a phenomenon called Hawking radiation. Given enough time, even the universe's most formidable monsters could whisper themselves out of existence. So while black holes are synonymous with violent stars ripped apart, space-time stretched like taffy, their shadows remind us that silence is just another form of communication. In the darkest corners of the cosmos, where chaos reigns supreme, the absence of light becomes a language all its own. Neutrinos are the universe's ultimate ghostwriters, particles so elusive they can pass through an entire planet like it's not even there. Picture this: trillions of them stream through your body every second, leaving no trace, like cosmic whispers you can't quite hear. But in the quietest places on Earth, like the pristine ice of Antarctica, scientists have built traps to catch these phantoms, turning silence into a superpower. The magic lies in their indifference. Unlike light, which gets absorbed, scattered, or bent by cosmic clutter, neutrinos barrel through galaxies, gas clouds, and even stars without slowing down. That means when we detect one, it's carrying a pristine message from some of the universe's most violent events: supernova, colliding black holes, or the jets of active galactic nuclei. It's like finding a letter sealed in glass, untouched by time or interference. That's why places like the Ice Cube Neutrino Observatory exist. Buried deep in the Antarctic ice, its sensors wait in perfect darkness for the rare moment a neutrino crashes into an atom, creating a faint blue flash called Cherenkov radiation. The ice isn't just a detector. It's a filter, blocking out cosmic rays and other noise so only the quietest, most distant signals get through. In 2017, IceCube caught a neutrino from a blazar 4 billion light-years away, a particle that had traveled since before Earth even formed. Its journey ended in a flash no brighter than a firefly, but the data it carried rewrote our understanding of cosmic rays and high-energy physics. What's even wilder is how these silent messengers defy expectations. When a star explodes, most of its energy isn't in the light show, it's in the neutrinos. The famous supernova 1987 released so many that detectors on Earth picked them up hours before the light arrived. Imagine getting a text from the universe saying, "Hey, something big just happened," before your eyes could even see it. That's the power of listening to the quiet. And the stories neutrinos tell aren't just about the past. Some theories suggest they might hold clues about dark matter or extra dimensions phenomena so subtle they're drowned out everywhere else. By chasing particles that treat planets like fog, we're learning to read the universe's faintest ink, written in a language only silence can translate. The next time you look up at the night sky, remember, the loudest explosions and the brightest stars are only half the conversation. The rest is happening in whispers, waiting for us to listen. Gravitational waves are the universe's way of turning silence into a microphone. Imagine throwing a pebble into a still pond. The ripples spread outward, carrying information about the splash without making a sound. That's exactly how these space-time distortions work, except the pond is the fabric of reality itself, and the pebble might be two black holes colliding with the energy of a billion suns. Yet the signal that reaches us is almost impossibly faint, a distortion smaller than the width of an atom stretched across miles of detectors. This is where silence becomes our greatest tool. Facilities like LIGO, the Laser Interferometer Gravitational Wave Observatory, are built to listen to these whispers, nestled in remote locations, shielded from earthquakes, traffic, even the rumble of ocean waves. These labs are so quiet they can detect vibrations 1,000 times smaller than an atomic nucleus. The key lies in their design: laser beams bouncing down vacuum-sealed tunnels, measuring the infinitesimal stretching and squeezing of space-time as a gravitational wave passes. It's like trying to hear a snowflake land in a hurricane, and yet we've done it. The first detection in 2015 wasn't just a triumph of engineering, it was a revelation. The signal came from two black holes, each dozens of times more massive than our Sun, spiraling into each other over 1 billion light-years away. For a fraction of a second, they released more energy than all the stars in the observable universe combined. But by the time those ripples reached Earth, they were quieter than a mouse's footsteps. What's astonishing isn't just that we heard it, but what the signal told us. The pitch and rhythm of the waves revealed the black holes' masses, their spins, even the precise moment they merged. Light could never show us that. And then there are neutron stars, SETI-sized remnants of dead stars so dense a teaspoon of their material would weigh 1 billion tons. When these cosmic marbles collide, they don't just send out gravitational waves, they also forge gold, platinum, and other heavy elements in their wake. Before LIGO, we could only guess how these metals ended up scattered across the cosmos. Now, by pairing gravitational wave detections with telescopes, we've watched the process unfold in real time. It's like witnessing alchemy in the dark with silence as our guide. What's truly humbling is how much we're still learning. Some gravitational waves might come from events we've never seen, cosmic strings, primordial black holes, even echoes of the Big Bang. Others could hint at flaws in Einstein's theory of relativity or reveal hidden dimensions. Every new detection is like tuning a radio to a station we never knew existed, picking up signals from the universe's most violent, most hidden corners. So the next time you think of silence as empty, remember, the quietest places are often the most alive with meaning. Gravitational waves don't just prove the universe is speaking, they show us how to listen. The Boötes Void isn't just empty, it's a cosmic anomaly that feels almost too big to exist. Stretching across 300 million light-years, this sprawling desert of space contains only a handful of galaxies, as if the universe forgot to fill in this particular corner. To put that in perspective, if our Milky Way were a single grain of sand, the Boötes Void would be a football field with just 3 or 4 grains scattered across it. Most voids are small, temporary gaps in the cosmic web, but this one is so vast and so eerily vacant that it's made scientists question everything from the distribution of matter to the very nature of dark energy. What makes this emptiness so unsettling is how it defies probability. According to our best models of the universe, regions this large shouldn't be this empty. It's like rolling a dice 1,000,000 times and never landing on a 6. Not impossible, but so unlikely it makes you wonder if the dice are loaded. Some theories suggest the void might be the aftermath of an ancient collision between bubble-like regions of spacetime during the universe's inflationary phase. Others speculate it could be a rare statistical fluke, a cosmic coincidence on a scale we're still struggling to comprehend. But the most tantalizing idea, that the Boötes Void is a window into something even stranger, perhaps an exotic form of dark energy or a flaw in our understanding of gravity itself. What's fascinating is how this silence forces us to innovate. To study the void, astronomers have to rely on the few galaxies that do call it home, using them as backlights to probe the emptiness between them. It's like trying to map a pitch-black room by watching how shadows move around a single candle. These observations have revealed subtle clues, hints of faint gas clouds or the gravitational tug of unseen dark matter, but the void's true nature remains elusive. And that's the real lesson of the Boötes Void. Sometimes the absence of something speaks louder than its presence. By studying what isn't there, we're learning how galaxies form, how dark energy shapes the cosmos, and even how our own models might need rethinking. This isn't just a hole in space, it's a mirror, reflecting back the limits of our knowledge and the audacity of our curiosity. The universe doesn't give up its secrets easily, but in the quietest places, it whispers the most provocative questions. Silence isn't just golden, it's the foundation of discovery. Think about the last time you tried to hear a whisper in a noisy room. It's nearly impossible. Now imagine that same challenge, but on a cosmic scale. That's why scientists seek out the quietest places on Earth, like the valleys of Guizhou in China, where the 500-meter aperture spherical telescope, or FAST, sits like a giant ear tuned to the universe's faintest murmurs. Nestled in a natural bowl of karst hills, this colossal dish is shielded from the radio chatter of human civilization, cell phones, satellites, even distant airplanes. The result, a listening post so sensitive it can detect the faint heartbeat of a pulsar thousands of light years away, or map the invisible threads of hydrogen gas weaving through the cosmos. What's remarkable isn't just the technology, it's the philosophy behind it. By eliminating interference, these radio quiet zones reveal signals that would otherwise be drowned out. Take pulsars, for example. These dense, spinning neutron stars emit beams of radio waves with the precision of atomic clocks. In a noisy environment, their rhythmic pulses blur into static. But in the silence of a place like Fast, they stand out like a metronome in an empty concert hall. Some of these pulsars are so stable that scientists use them to test Einstein's theory of relativity, watching for tiny hiccups in their timing that might betray the presence of gravitational waves. Others serve as cosmic lighthouses, helping us navigate the galaxy's structure. Then there's neutral hydrogen, the universe's most abundant element and a ghostly tracer of cosmic architecture. Emitting a faint radio signal at a wavelength of 21 centimeters, this gas is invisible to optical telescopes, but in radio silence, it glows like a fingerprint, revealing the hidden skeleton of galaxies and the vast rivers of matter flowing between them. Without the quiet, these signals would vanish into the background noise of the cosmos, like a single voice lost in a stadium. But the real magic happens when silence unveils the unexpected. In 2020, FAST detected a repeating fast radio burst, a mysterious high-energy pulse from deep space. Most bursts are one-offs, but this one kept echoing across the void. Was it a neutron star's cry, a black hole's tantrum, or something entirely unknown? The only way to find out was to listen, really listen without the distractions of Earth's electronic buzz. This is the paradox of cosmic silence. The less noise we make, the more the universe speaks. It's not about hearing absence, it's about creating the conditions for revelation. Every time we carve out a pocket of quiet, whether in a remote valley or the vacuum of space, we're not just turning down the volume. We're tuning in to a frequency where the cosmos tells its deepest secrets, one whisper at a time. Far beyond the orbits of Neptune and Pluto, where sunlight fades to a dim twilight, lies a frozen graveyard of the solar system's infancy, the Oort Cloud. This colossal shell of icy debris stretches nearly a light year into space, a vast no-man's land where temperatures hover just above absolute zero. Unlike the asteroid belt or the Kuiper belt, this region isn't cluttered with rocky fragments or dwarf planets. Instead, it's a diffuse swarm of pristine ice chunks, some no larger than a city block, drifting in near-perfect stillness. What makes the Oort Cloud so extraordinary isn't just its distance, it's its silence. Shielded from the gravitational tugs of planets and the heat of the sun, these icy relics have remained virtually unchanged since the solar system's birth over 4.5 billion years ago. They're cosmic time capsules, preserving the raw materials that once swirled in the protoplanetary disk. When a comet like Hale-Bopp or Hyakutake streaks through the inner solar system, blazing a trail across our night sky, we're essentially witnessing a piece of the Oort Cloud thawing out, offering us a taste of the solar system's original recipe. But studying this silent frontier is like trying to spot a snowflake in a blizzard from 1,000 miles away. The Oort Cloud's objects emit no light of their own, reflect almost no sunlight, and drift so sparsely that a spacecraft could pass through without encountering a single one. So how do we detect them? The answer lies in patience and precision. Astronomers wait for the rare moments when a distant star's light flickers, not because of the star itself, but because an Oort Cloud object has drifted in front of it, casting a shadow too faint for most telescopes to see. It's detective work on an interstellar scale, relying on the absence of noise to reveal what's hiding in plain sight. The Oort Cloud's quiet also holds clues to one of astronomy's biggest mysteries, the origin of Earth's water. Some theories suggest that comets from this distant reservoir delivered water to our planet during the solar system's chaotic early days. By analyzing the chemical fingerprints of these icy visitors, scientists can trace whether their hydrogen isotopes match the water in our oceans. But here's the twist: not all comets tell the same story. Some, like those from the Kuiper belt, don't quite match Earth's water signature. That leaves the Oort Cloud as the prime suspect, a silent witness to the cosmic robbery that may have filled our oceans. Perhaps the most haunting idea is that the Oort Cloud isn't entirely ours. Computer simulations suggest some of its icy inhabitants could be interstellar interlopers, objects captured from other star systems as they drifted through the Milky Way. If true, this means the solar system's outermost reaches might be a library of frozen artifacts from across the galaxy, waiting in the dark for us to decode them. The Oort Cloud doesn't give up its secrets easily. Unlike Mars or Jupiter, it can't be studied with rovers or orbiters, at least not yet. Its whispers are too faint, its signals too sparse. But that's the beauty of it. In a universe that often shouts, the Oort Cloud reminds us that some truths only reveal themselves to those willing to embrace the quiet, to listen for the nearly nothing, and to trust that even the emptiest spaces have stories to tell. For decades, we've been straining our cosmic ears, listening for any whisper of intelligence beyond Earth. Projects like SETI, the search for extraterrestrial intelligence, have scanned the skies with radio telescopes, hunting for patterns in the noise, for signals that scream artificial. Yet all we've heard is silence, not just ordinary silence, but a deafening, universe-spanning quiet that seems to defy logic. If life is so common, if intelligence arises as naturally as stars do, where is everybody? This eerie absence has a name, the Fermi paradox, and it's one of the most unsettling puzzles in science. But here's the twist: what if the silence isn't an absence at all? What if it's a message? Some scientists argue that advanced civilizations might deliberately avoid broadcasting their presence. Think of it like walking through a nature reserve. You observe quietly, careful not to disturb the ecosystem. This idea, called the zoo hypothesis, suggests we might be living in a kind of cosmic conservation zone, where older, wiser species have chosen not to interfere. Or perhaps they're communicating in ways we haven't even thought to look for, using neutrino beams or quantum entanglement instead of radio waves. Then there's the dark forest theory, which paints a far more cautious picture. Imagine the universe as a vast, shadowy woodland where every civilization hides, afraid to reveal itself. In this scenario, any species that announces its location risks attracting predators or rivals. Silence becomes survival. It's a chilling thought that the cosmos might be teeming with life, but everyone's too afraid to speak up. But let's not jump to the darkest conclusions just yet. There's another possibility. We might simply be early. The universe is 13.8 billion years old, but Earth didn't form until about a third of that time had passed. Intelligent life could still be rare, still evolving elsewhere while we're out here waving our metaphorical flashlights into the void. Or maybe we're looking for the wrong things. Our search assumes aliens would use technology similar to ours, but what if their radio signals are as incomprehensible to us as a dolphin's sonar is to a tree? The silence itself is teaching us something profound about humility, about the limits of our assumptions, and about how much we still have to learn. Every empty frequency band, every star system that doesn't answer back, is a nudge to think differently. Maybe we're alone, maybe we're not, but either way, the quiet is anything but empty. It's a mirror reflecting back our own hopes, fears, and the vastness of what we don't yet understand. And that makes the search itself one of humanity's most beautiful experiments, a conversation with the unknown, where every unanswered call is still a kind of reply. At the smallest scales imaginable, silence isn't just an absence of sound, it's a microscope for reality itself. Picture space-time not as a smooth, unbroken fabric, but as a shimmering mosaic of unimaginably tiny grains, each a billion times smaller than an atom. This is the wild frontier of loop quantum gravity, where physicists propose that the universe might be pixelated at its core, like a cosmic photograph zoomed into its maximum resolution. But how do you detect something that infinitesimal? The answer lies in some of the quietest places on Earth, where scientists hunt for whispers of this quantum structure in the void between vibrations. To understand why silence matters, think of trying to measure the ripples in a pond while someone's tossing boulders into it. Everyday noise, footsteps, passing trucks, even the hum of electricity would drown out the delicate tremors of spacetime's quantum foam. That's why experiments like the Fermilab holometer or the future Einstein telescope are buried deep underground or suspended in vacuum chambers, shielded from the faintest disturbances. These aren't just sensitive instruments, they're cosmic silencers designed to mute the world so the universe's faintest murmurs can be heard. The stakes couldn't be higher. If spacetime is indeed granular, it would rewrite our understanding of reality, bridging the gap between Einstein's relativity and the quantum realm. Some theories suggest these tiny pixels of spacetime could create subtle jitters in the path of laser beams or cause particles to wobble in ways that defy classical physics. But detecting those effects requires measuring distances smaller than a proton's width over miles of space, a task so precise it's like trying to spot a single grain of sand shifting on the moon. What's fascinating is how these experiments turn silence into a tool. By eliminating all vibration, researchers create conditions where even the universe's finest structures can't hide. It's like tuning a radio to a frequency where static fades away, leaving only the faintest signal, a signal that might carry the signature of spacetime's true nature. And if that signal appears, it won't just answer a question. It'll open a door to a new frontier where the quietest places in existence reveal the universe's loudest truths. What if the emptiest places in our universe aren't just gaps, but bruises? Cosmic voids, those sprawling deserts of near-nothingness, might hold scars from collisions with other universes. It's a wild idea, but one that's gained traction among physicists exploring the multiverse. Picture our universe as a bubble floating in an infinite foam, where other bubble universes drift just beyond our perception. When these bubbles brush against each other, the impact could leave faint imprints in the cosmic microwave background, those whisper-thin temperature variations we detect in the quietest voids. Think of it like pressing your hand against a foggy window. The mark lingers long after the touch is gone. The evidence, if it exists, would be subtle. Imagine sifting through static on an old TV, searching for a pattern that doesn't belong. Some researchers argue that certain cold spots in the CMB, like the notorious cold spot in the constellation Eridanus, could be cosmic fingerprints from such a collision. These anomalies are just a few millionths of a degree cooler than their surroundings, but in a universe where silence amplifies every clue, even that faint chill could be revolutionary. It's like finding a single mismatched thread in a tapestry light years wide, a tiny flaw that hints at a much bigger story. Of course, this isn't the only explanation for these cold spots. They could be statistical flukes or artifacts of how we map the sky, but the multiverse theory offers something tantalizing, a way to test the untestable. If voids really are the universe's quietest witnesses, their silence might be the perfect medium for echoes from beyond our cosmic horizon. Future telescopes, like the Simons Observatory or the next-generation CMB experiments, could hunt for these ghostly signatures with unprecedented precision. What's breathtaking is the scale of the idea. A single void might be the closest thing we have to a window into another reality, a place where the rules of physics could be utterly alien. Maybe in those other universes, gravity works backwards or time flows in loops. The voids don't judge, don't interfere. They simply hold space for possibilities we're only beginning to imagine. So while the multiverse remains speculative, the voids remind us of a profound truth. sometimes the most important discoveries aren't about what's there, but what isn't. In the quiet between galaxies, in the cold spots where the universe seems to pause, we might just find the fingerprints of existence itself, proof that we're not alone in the cosmic foam, but part of something vast, strange, and beautifully unknowable. There's a profound irony in how the universe builds the ingredients for life, not in the chaos of stellar nurseries or the fury of supernova, but in the hushed corners where nothing seems to happen at all. Drifting between the stars, shielded from harsh radiation and violent collisions, tiny molecules begin a delicate dance. In these silent pockets, atoms of hydrogen, carbon, and oxygen meet and bond, forming compounds like water, formaldehyde, and even amino acids, the very Lego bricks of biology. It's a process so quiet you could miss it if you blinked, yet without these invisible factories, life as we know it wouldn't exist. Take the dark molecular clouds, for instance. These colossal, icy structures are so dense that not a single photon of starlight pierces through. To the naked eye, they're just black smudges against the Milky Way. But inside that darkness, temperatures hover just a few degrees above absolute zero, creating the perfect lab for chemistry. Here, cosmic rays, the universe's subtlest energy source, nudge atoms together, forging molecules too fragile to survive anywhere else. It's like trying to build a house of cards in a hurricane versus a windless room. The silence isn't just convenient, it's essential. And then there's the magic of ice. On dust grains floating in these clouds, water molecules freeze into crystalline lattices, trapping other compounds in their embrace. This icy scaffolding protects fragile molecules from destructive radiation, letting them grow more complex over millions of years. Some of these icy grains eventually drift into newborn planetary systems, seeding young worlds with probiotic material. Imagine that, the frost on a window pane in deep space might hold the blueprint for life itself. But silence doesn't just preserve, it also transforms. In the voids between galaxies, where distances are so vast that stars appear only as faint pinpricks, something extraordinary happens. The lack of nearby radiation allows hydrogen atoms to cool and clump together, forming vast, diffuse reservoirs of gas. Over eons, gravity pulls these quiet pools into filaments, weaving the cosmic web that guides galaxy formation. Without these silent threads, the universe would be a scattered mess of stars, never coalescing into the structured beauty we see today. Even on planetary scales, stillness plays a role. Consider Earth's early oceans, shielded from the sun's deadly ultraviolet rays by a primitive atmosphere. In those quiet waters, free from the bombardment of meteorites or the churn of volcanic vents, simple molecules could experiment, combining and recombining until, by some improbable accident, they sparked life. It's no coincidence that the deepest, most silent parts of our oceans still host ecosystems unlike anywhere else on the planet, thriving in conditions that mimic those ancient seas. What's breathtaking is how this delicate balance hinges on absence. Too much noise, too much radiation, too many collisions, and the fragile dance falls apart. But in the quiet, the universe whispers its recipes, assembling complexity from simplicity, order from chaos. The next time you gaze at the night sky, remember, the brightest stars might catch your eye, but it's the darkness between them where the real work happens. Silence isn't empty, it's the universe's most patient architect. The vast silence of deep space isn't just empty, it's a lifeline. Take Voyager 1, humanity's farthest flung messenger, now drifting beyond the solar wind's reach in interstellar space. Its signal, barely stronger than a refrigerator light bulb, travels over 14 billion miles to reach us. That whisper, weaker than a smartphone's radio by a factor of 20 billion, only gets through because the cosmos is so unimaginably quiet. Without the vacuum's perfect hush, its transmissions would vanish like a shout in a hurricane. Yet this silence is a paradox. The same emptiness that lets Voyager's faint pings reach Earth also makes interstellar communication agonizingly slow. A single command sent to the spacecraft takes nearly a full day to arrive, and another day for its response to crawl back. Imagine trying to have a conversation where each reply takes 2 days. That's the reality of exploring the void. Silence both enables and throttles our reach into the cosmos. What's fascinating is how we've weaponized this quiet. NASA Deep Space Network, a trio of colossal radio dishes in California, Spain, and Australia, acts like a galactic ear trumpet. These facilities sit in remote valleys, shielded from earthly chatter, their receivers chilled to near absolute zero to minimize electronic noise. Every watt of power, every byte of data from distant probes like New Horizons or Juno is extracted from the cosmic static with the precision of a safecracker listening for tumblers. But silence isn't just a technical hurdle, it's a canvas for discovery. When the Cassini probe skimmed Saturn's rings, its radio signals passed through the particles, revealing their size and density by how they scattered the waves. The quieter the background noise, the clearer these subtle distortions became. It's like diagnosing a patient by listening to their heartbeat in a soundproof room versus a busy street. The silence of space turns spacecraft into stethoscopes, letting us hear the universe's hidden rhythms. And then there's the future. Breakthroughs like laser communications tested by NASA's Psyche mission could turn silence into a superhighway. By encoding data in photons instead of radio waves, we might one day stream 4K video from Mars with less lag than a Zoom call. But even lasers rely on the void's stillness. A single dust particle or wandering atom could scatter the beam into noise. The cleaner the silence, the crisper the signal. Perhaps the most poetic twist is how this quiet connects us. Every image of Pluto's heart-shaped plains, every whisper of solar wind from Voyager, every pixel of the Martian sunset from Perseverance, they all ride the same silent carrier wave across the abyss. In a universe where sound can't travel, we've learned to shout with light, turning emptiness into the ultimate messenger. The next time you look up at the stars, remember, the darkness between them isn't just space, it's the quietest, most powerful bridge we'll ever build. The hush between the stars has always been more than just empty space, it's a mirror reflecting humanity's deepest questions. Ancient civilizations gazed into the void and saw gods, ancestors, or the breath of creation itself. The Aboriginal peoples of Australia traced songlines through the dark, mapping not just the land but the cosmos, turning silence into story. The Maya watched the black expanse between Venus and the Sun, calculating sacred cycles with precision that still astounds astronomers today. To them, silence wasn't absence, it was the canvas of meaning. Fast forward to modern science, and that same silence becomes a different kind of language. When radio telescopes point at seemingly empty patches of sky, they're not just listening for absence, they're decoding the universe's fine print. The cosmic microwave background's faint static. That's the afterglow of creation, a baby picture of the cosmos. The gravitational waves rippling through space-time, they're the universe's way of showing its bones. What ancient cultures revered as sacred, scientists now pass as data, revealing how stars ignite, galaxies collide, and space-time stretches, yet the duality remains. The more we learn about cosmic silence, the more it humbles us. Take quantum vacuum fluctuations, those ghostly particles popping in and out of existence in empty space. They're not just physics, they're philosophy in motion. If a void can team with temporary universes, what does that say about our own reality? Are we just one fluctuation in an infinite sea of possibilities? Even the great silence of SETI unanswered calls forces us to confront whether we're alone, overlooked, or simply asking the wrong questions. Perhaps silence is the universe's way of keeping secrets until we're ready to understand them. When 18th century astronomers first mapped the empty space between stars, they couldn't have imagined it was filled with dark matter. When Einstein wrote his equations, he didn't foresee that the cosmological constant he dismissed would return as dark energy. Every era's silence holds truths the next generation learns to hear, so the next time you look up at the night sky, don't just see the darkness between the stars, listen to it. That quiet is the oldest teacher we have, whispering across time in a language we're still learning to speak. Whether through myth or math, the message is the same. Silence isn't the end of the conversation. It's the invitation to lean closer. The next generation of telescopes won't just see farther, they'll listen deeper. Take the James Webb Space Telescope, perched 1 million miles from Earth at Lagrange Point 2. Unlike its predecessors, Webb doesn't just block out city lights, it escapes Earth's entire thermal hum, chilling its instruments to -380 degrees Fahrenheit. That cold, silent vantage point lets it detect the faintest infrared whispers from the universe's first galaxies, light that's been stretched into near nothingness by cosmic expansion. But here's the kicker: Webb's most revolutionary discoveries might come from what it doesn't see. When it stares at seemingly empty patches of sky for days, it's not just hunting for bright objects, it's revealing the dark, quiet scaffolding between them where primordial gas and stealthy exoplanets hide. Then there's LISA, the Laser Interferometer Space Antenna, a trio of spacecraft set to launch in the 2030s. While ground-based detectors like LIGO strain to hear gravitational waves through Earth's seismic noise, LISA will float 2.5 million kilometers apart in perfect formation, laser beams threading the void between them. Without atmospheric interference or tectonic rumbles, it'll catch low-frequency ripples from events no earthly instrument could detect, like the slow-motion mergers of supermassive black holes, a bass note so deep it takes years to play out. These waves carry secrets about how galaxies evolve, hidden in the quietest frequencies of spacetime itself. But silence isn't just about escaping noise, it's about creating new ways to see. The upcoming Nancy Grace Roman Space Telescope will use a technique called microlensing to spot rogue planets, worlds adrift in the darkness between stars. By monitoring how these unseen objects bend the light of distant stars, Roman can map a population of planets that emit no light of their own. It's like finding footsteps in fresh snow long after the hiker has gone. Similarly, the Square Kilometre Array, a radio telescope network spanning continents, will tune into the universe's cold hydrogen, the silent residue of the Big Bang, to trace how galaxies siphon gas from the voids around them. What unites these missions is their reliance on cosmic quiet as a tool. The farther we push into the void, the more we realize that emptiness is a lens, sharpening our view of reality's finest details. Future telescopes won't just show us new wonders, they'll teach us to listen to the spaces between them, where the universe's oldest truths are written in the language of silence. And that's the ultimate irony: the answers we seek aren't hidden in the noise. They've been waiting all along in the quiet for instruments sensitive enough to hear them. Light from the early universe doesn't just fade, it gets lost in the noise. Imagine trying to hear a centuries-old song playing on a scratched record, buried under layers of static. That's what happens to ancient photons as they travel through crowded galactic neighborhoods, getting scattered, absorbed, or drowned out by younger, brighter stars. But in the quietest voids of space, where galaxies are few and far between, these primordial whispers travel undisturbed, like a letter sealed in cosmic amber. Take the farthest quasar we've ever spotted, J03, 1806, whose light began its journey just 670 million years after the Big Bang. By the time those photons reached Earth, they'd been stretched into infrared waves by the universe's expansion, a 13-billion-year-old telegram written in the language of redshift. But here's what's extraordinary. The clarity of that signal depends entirely on the emptiness it crossed. Had it passed through dense galaxy clusters or nebulae, its fingerprints would have been smudged beyond recognition. Instead, the void preserved its purity, letting us read the chemical composition of the early cosmos as clearly as a lab sample. This isn't just about distance, it's about fidelity. When astronomers study the Lyman alpha forest, those delicate absorption lines in a quasar's spectrum, they're essentially reading cosmic tea leaves. Each dip in the light reveals where neutral hydrogen gas once blocked its path, mapping the universe's structure during the dark ages before stars ignited. But these patterns only stay sharp if the light hasn't been muddied by later interactions. The quieter the path, the crisper the snapshot of history. Some of the most profound revelations come from what isn't there. The Gunn-Peterson trough, a telltale gap in certain wavelengths of quasar light, proves the universe was once so thick with hydrogen that it absorbed nearly all ultraviolet radiation. That epoch ended when the first stars and galaxies ionized the gas, clearing the cosmic fog. But we'd never know that if later starlight hadn't been filtered through pristine voids, preserving the signature of that transformation like a fossil in crystal. Even the cosmic microwave background, the oldest light we can detect, owes its legibility to silence. Those faint temperature variations, smaller than 1 part in 100,000, would have been erased if the universe hadn't expanded into a near-perfect vacuum, freezing those primordial fluctuations in place. It's as if the cosmos knew we'd need a clean slate to decode its origins. What's humbling is how much we still miss. For every ancient photon that reaches us untouched, countless others get scrambled beyond recovery. But the voids give us a fighting chance, acting as cosmic archivists that shelf the universe's oldest records in the quietest corners. The next time you see a dark patch in the night sky, remember, it's not an empty space. It's a time machine holding light that outlasted galaxies, stars, and entire eras waiting for us to listen. The universe has a soundtrack, but you'd need the silence of deep space to hear it. Buried in the vast, empty stretches between galaxies are echoes of the cosmos' earliest moments, when it wasn't silent at all. Picture the newborn universe not as a still void, but as a seething, roiling plasma, dense enough to carry sound waves. Those waves, ripples of pressure moving at half the speed of light, were the universe's first symphony, a deafening roar trapped in the hot soup of particles. Then, as space expanded and cooled, the music stopped abruptly. The waves froze in place, leaving behind a ghostly imprint in the distribution of matter. Today, we call these relics Barrian acoustic oscillations, and they're the closest thing we have to a cosmic fossil of sound. What's astonishing is how these ancient vibrations shaped everything we see. As the universe expanded, those frozen waves became templates for structure. Matter clumped along their peaks and troughs, eventually forming galaxies that inherited this rhythm. The result, a universe where galaxies aren't scattered randomly but are spaced with eerie regularity, like beads on a string. In crowded regions, this pattern gets blurred like trying to hear a melody in a crowded subway. But in the quiet voids where galaxies are sparse, the signal stands out with breathtaking clarity. It's as if the universe left us a fingerprint, and the emptiest places preserved it best. Mapping these oscillations is like listening to a record playing at the wrong speed. By measuring the average distance between galaxy clusters, about 500 million light-years, scientists can reconstruct the original note the universe played. That scale isn't arbitrary. It's the exact distance those sound waves could travel before the cosmos cooled and silenced them. The quieter the patch of sky, the sharper the measurement. Projects like the Sloan Digital Sky Survey have turned this cosmic echo into a ruler, letting us gauge the universe's expansion with precision. But the real magic lies in what else these whispers reveal. The spacing of these oscillations depends on the tug-of-war between dark matter's gravity and dark energy's push, meaning the universe's quietest corners are also its most sensitive scales. Yet there's a twist. Some of these frozen waves don't quite match our models. In certain voids, the spacing seems slightly off, as if the universe hit a sour note. Could this be evidence of exotic physics, extra dimensions, modified gravity, or some unknown dark sector particle? Or is it just cosmic static we haven't learned to filter out? The answers might lie in even quieter observations, like the upcoming DAISY survey, which will map millions of galaxies to hear these echoes in unprecedented detail. What's humbling is how much this soundless music tells us. Those oscillations are more than fossils. They're a live feed from the universe's infancy, a time when everything was too hot for atoms, let alone stars. By studying the silence between galaxies, we're not just mapping space, we're replaying the first moments of time itself. And the quieter we listen, the clearer the melody becomes. Silence might be the universe's greatest puzzle, especially when it comes to the Fermi paradox. If the cosmos is teeming with life, why does it feel like we're the only ones shouting into the void? One possibility is that we're not listening the right way. Imagine trying to tune into a radio station with a telescope. You'd hear nothing, not because the station isn't broadcasting, but because your tools don't match the signal. Advanced civilizations might have moved beyond radio waves, communicating through channels we're only beginning to understand, like neutrino beams or quantum entanglement. These aren't sci-fi fantasies. Neutrinos are real particles that slice through planets effortlessly, and quantum networks could transmit information instantaneously across light years. If aliens are using such technologies, our current searchers would miss them entirely, like trying to spot a laser pointer in broad daylight. Then there's the timing problem. Human civilization has only been broadcasting detectable signals for about a century, a blink in cosmic terms. Meanwhile, the universe has been around for nearly 14 billion years. Other civilizations might have risen and fallen long before we even existed. Their signals already faded into the background hum of space. Or perhaps they're still out there, but their transmissions are so brief or infrequent that we haven't caught them yet. Think of it like two ships passing in the night. If their lanterns only flash once every 1,000 years, the chances of seeing each other are vanishingly small. But the most intriguing idea is that silence is intentional. Some theories suggest advanced species might avoid broadcasting their presence to evade potential threats. In a universe where predators could lurk among the stars, staying quiet might be the ultimate survival strategy. Others propose that civilizations eventually transition inward, building virtual realms or harnessing the energy of black holes, leaving no trace for outsiders to find. It's like ants trying to understand the internet. Their world simply lacks the framework to comprehend what lies beyond it. The paradox isn't just about absence, it's about perspective. Our search assumes aliens think like us, communicate like us, and value the same things we do. But what if they're so profoundly different that their very existence is invisible to our methods? The silence isn't empty, it's a mirror reflecting the limits of our imagination. Every unanswered call, every quiet patch of sky, is a challenge to think bigger, listen harder, and reconsider what it means to not be alone. Black holes don't just swallow light, they threaten to erase the very fabric of reality. At first glance, the math seems clear. Anything crossing a black hole's event horizon vanishes forever, crushed into a singularity where space, time, and even the laws of physics break down. But here's the problem: quantum mechanics insists that information can never truly be destroyed. Every particle, every interaction leaves a trace, like a cosmic fingerprint. So what happens when these two rules collide? That's the black hole information paradox, a puzzle so profound it split physicists for decades. The conflict cuts to the heart of how we understand the universe. On one side, Einstein's general relativity paints black holes as perfect cosmic erasers, where information is shredded beyond recovery. On the other, quantum theory argues that even if information gets scrambled, it must still exist somewhere. Imagine burning a book, the pages turn to ash, but in theory, if you could track every molecule of smoke and heat, you could reconstruct every word. Black holes seem to break that principle, leaving us with an impossible choice. Either our understanding of gravity is flawed, or quantum mechanics is incomplete. But there's a tantalizing solution hiding in the silence of the event horizon. The holographic principle suggests that all the information swallowed by a black hole isn't lost, it's smeared across its surface like a cosmic projector screen. Think of it like a 3D movie encoded on a 2D film. The event horizon, that seemingly smooth boundary, might be buzzing with quantum bits, preserving every detail of what fell in. This isn't just theoretical sleight of hand. Calculations show that the horizon's area correlates precisely with the black hole's entropy, a measure of its hidden information. The implications are staggering. If holography is correct, then the quietest surface in the universe, the event horizon, is actually the loudest hard drive, storing data in ways we're only beginning to decode. Experiments with quantum entanglement, like those testing the firewall paradox, hint at this duality. When particles become entangled near a black hole's edge, their linked states might encode information about the interior, like a quantum Rosetta Stone. Yet mysteries remain. How exactly does information escape a black hole if nothing can? Some theories point to Hawking radiation, the faint glow predicted to leak from black holes over eons. This radiation might carry scrambled traces of what fell in, like a message in a bottle tossed from a prison cell. Others propose even wilder ideas, like black holes birthing new universes, where the information resurfaces in an entirely different reality. What's clear is that the paradox isn't just about black holes. It's a battleground for the soul of physics. Solving it could bridge the gap between quantum mechanics and gravity, revealing a deeper theory that unites all forces. And the key lies in the quiet, the stillness of the event horizon, the hush of Hawking radiation, the silent dance of entangled particles. The universe's loudest answers aren't shouted. They're whispered, waiting for us to lean in and listen. Dark energy doesn't announce itself with fireworks or collisions. It reveals its presence in the quietest stretches of cosmic emptiness. Picture a vast void between galaxies, where stars are so sparse that light itself seems hesitant to cross. It's here, in these near-perfect silences, that scientists catch glimpses of the universe's most elusive force. The key lies in supernova, exploding stars so brilliant they outshine entire galaxies for weeks. But not just any supernova. To measure dark energy's subtle push, astronomers seek out those rare explosions that ignite far from the crowded galactic centers, where the cosmic background hum fades to a whisper. Why does silence matter? Because dark energy's signature is absurdly faint. It's not a tug or a shove, but a gentle, relentless pressure, like a breeze so light you'd miss it in a storm. In the noisy heart of galaxy clusters, where gravity twists space-time and interstellar dust scatters light. That signal gets drowned out. But in the voids where space is clean and still, the light of distant supernova arrives undistorted, carrying pristine clues about how fast the universe was stretching when they detonated. It's like trying to measure the expansion of a balloon by watching confetti inside easier if the confetti isn't being tossed around by other forces. The revelations from these quiet observations are staggering. In the late 1990s, two teams studying these lonely supernova made a discovery that upended cosmology. The universe isn't just expanding, it's accelerating. The emptiest patches of space held the clearest evidence that some invisible energy, was working against gravity's pull. They called it dark energy, not because it's sinister, but because it refuses to interact with light or matter in any way we can directly detect. Its only fingerprint, the way it stretches the cosmos itself, like an unseen hand tugging at the fabric of reality. But the deeper mystery lies in the pattern. The quieter the region, the more dark energy dominates. In the densest parts of the universe, gravity fights back, binding galaxies into clusters and filaments. But in the voids where matter is scarce, dark energy's influence grows unchecked, pushing space apart faster and faster. It's as if the universe has a built-in amplifier. The emptier it gets, the louder dark energy's effect becomes. Future telescopes like the Vera Rubin Observatory plan to map millions of these distant supernovae, using the voids as cosmic soundproof chambers to isolate dark energy's whisper from the universe's noise. What's haunting is the implication. If dark energy keeps winning, the universe's fate might be a silence so profound it chills. Galaxies will drift beyond each other's horizons, their light stretched into invisibility. New stars will stop forming. The cosmos will grow colder, darker, emptier, until even the echoes of the Big Bang fade into nothingness. But for now, in these quiet corners, we're learning to listen. And the message is clear: the universe isn't just expanding, it's running away from itself, driven by a force we can only measure when everything else goes still. There's a reason the silence of space feels so unsettling. It clashes with everything our brains are wired to expect. On Earth, silence usually means absence, an empty room, a paused conversation, a power outage. But the cosmic void isn't empty at all. It's a bustling arena of quantum fluctuations, gravitational ripples, and dark matter weaving unseen structures. Our discomfort comes from a primal mismatch. We evolved to interpret rustling leaves as potential threats and distant voices as signs of community. A universe that speaks in particle decays and redshifted light doesn't just confuse us. It triggers a deep-seated unease, like standing in a forest where the trees don't whisper back. This tension between perception and reality reveals a fascinating truth. Human intuition breaks down at cosmic scales. We're brilliant at judging the speed of an approaching car or the ripeness of fruit, but our brains short-circuit when confronted with phenomena like quantum entanglement or the sheer size of intergalactic voids. It's why early astronomers imagined celestial spheres grinding like clockwork, and why even today, black holes are often depicted as swirling drains. We default to familiar metaphors because the truth feels alien. Cosmic silence doesn't just hide secrets, it exposes the limits of our mental toolbox. Yet this disconnect is also an invitation. Learning to hear the universe's subtle language means embracing tools beyond our senses. Radio telescopes translate electromagnetic whispers into sound we can process. Gravitational wave detectors turn space-time tremors into audible chirps. Even the cosmic microwave background, that faint afterglow of the Big Bang, gets sonified into haunting chords for public lectures. These aren't just gimmicks, they're bridges between the universe's quiet truths and our noisy, earthbound brains. The more we listen this way, the more we realize that silence was never silent. It's a symphony playing in a register we're only beginning to tune into. Consider how differently cultures interpret silence. In many indigenous traditions, quiet isn't absence but presence, a space for ancestors, spirits, or the land itself to speak. The Maori concept of tangi embraces silence as a form of deep communication, while Japanese aesthetics prize ma, the pregnant pause between sounds. These perspectives hint at a radical idea. Maybe the problem isn't cosmic silence, but our limited definition of listening. If we could shed our bias toward auditory noise, we might recognize that the universe communicates constantly, through the spin of particles, the curl of space-time, even the way galaxies align like compass needles pointing to unseen forces. The challenge and the thrill is rewiring our intuition without losing our humanity. Astronomers training to analyze telescope data often describe a eureka moment when raw numbers transform into visceral understanding. It's like learning to read a new language where punctuation marks are gravitational lenses and verbs are spectral lines. This mental shift doesn't erase wonder, it deepens it. Suddenly, the quiet between stars isn't eerie, it's electric with potential, humming with equations waiting to be decoded. The same void that once felt like a cosmic shrug becomes a chalkboard scrawled with clues. So the next time you feel unsettled by the universe's quiet, remember, you're not hearing nothing. You're standing at the edge of a new kind of literacy, where silence isn't the end of the conversation, but the start of a much bigger one. The cosmos isn't mute, we're just learning how to listen. Silence might be the ultimate biosignature. When we imagine life beyond Earth, we often picture lush alien jungles or glowing cities, scenes bursting with noise and activity. But the reality could be far subtler. Some of the best candidates for harboring life are places where stillness reigns, where the absence of chaos creates the perfect cradle for biology. Take red dwarf stars, for example. These dim, cool stars make up 70% of the stars in our galaxy, yet they're so faint you could stare right at one and barely notice. But their quiet nature is precisely what makes them intriguing. Unlike our sun, which flares violently and bathes its planets in harsh ultraviolet radiation, red dwarfs offer something rare in the cosmos: stability. Their habitable zones, the regions where liquid water could exist, are so close that planets become tidally locked, with one side perpetually facing the star. That might sound extreme, but in the gentle, unwavering glow of a red dwarf, life could find a rhythm undisturbed by seasons or solar storms. Then there's the silence of ice. Beneath the frozen crusts of moons like Europa and Enceladus, vast oceans slosh in perpetual darkness, shielded from the deadly radiation of space. These aren't the vibrant, sunlit seas of Earth, but something far stranger: worlds where the only energy comes from hydrothermal vents or the slow flexing of tidal forces. In such environments, life wouldn't need sunlight. It might cling to rocky outcrops near volcanic plumes or drift in slow currents, metabolizing chemicals we'd consider poison. The Cassini spacecraft spotted plumes of water vapor erupting from Enceladus, hinting at a subsurface ocean rich in organic molecules. If life exists there, it's not shouting, it's whispering, hidden beneath miles of ice, in a darkness so complete it makes the deep sea look bright. Even on Earth, some of the hardiest organisms thrive in silence. In caves where sunlight never reaches, bacteria derive energy from rocks. In Antarctic lakes buried under glaciers, microbes persist in water colder than your freezer. These extremophiles don't just survive in quiet, hostile environments, they flourish. If life on our planet can cling to existence in such marginal places, why not on a frozen moon or a rogue planet drifting between stars? The universe's quiet corners might not just shelter life, they could be its preferred habitat. The search for extraterrestrial life often focuses on what we can see: oxygen in an atmosphere, the glow of chlorophyll, the radio signals of a technological civilization. But the deeper lesson might be to listen for what we can't. Life could be thriving in the shadows, beneath ice, or in the steady light of a dim star, where silence isn't absence, it's an evolutionary advantage. The next time you look up at the night sky, remember, the most promising places to find life might be the ones we least expect, hiding in plain sight, waiting in the quiet. Humanity has always been a noisy species, building, broadcasting, reaching out into the void with every tool at our disposal. But as our presence in space grows, so does an invisible pollution we rarely consider: the slow erosion of cosmic silence. Every satellite beaming data, every radio signal leaking from Earth, every probe chattering back to mission control adds to a growing static that could one day drown out the universe's subtlest signals. It's not just about avoiding annoyance, it's about preserving the very conditions that let us learn. Imagine trying to study a butterfly's wing beats while standing in a hurricane. That's the challenge future astronomers might face if we don't start thinking differently about our cosmic noise footprint. The stakes are higher than most realize. Take the search for extraterrestrial intelligence. SETI researchers sift through radio static for patterns that might betray an alien civilization, but human-made interference already complicates their work. Stray signals from satellites, TV broadcasts, and even microwave ovens have masqueraded as false positives, sending scientists on wild goose chases. Worse yet, as mega-constellations like Starlink blanket the sky with thousands of satellites, their radio emissions create a persistent haze that could obscure genuine cosmic whispers. It's ironic our attempts to connect might sever our ability to listen, but the problem goes beyond alien hunting. The same quiet that lets SETI eavesdrop on potential neighbors also allows radio astronomers to peer into the universe's formative years. Hydrogen, the most abundant element in existence, emits a faint radio signal at 21 centimeters, a wavelength that's become crucial for mapping the cosmos's structure. When human noise encroaches on this frequency band, it's like spilling ink across a priceless manuscript. Already, astronomers have had to abandon once pristine radio quiet zones as terrestrial interference creeps in. The proposed lunar far-side telescope, shielded by the moon itself from Earth's chatter, might be our last chance to hear the universe's oldest stories without static. This isn't just a scientific dilemma, it's an ethical one. We're the first species capable of altering the cosmic soundscape beyond our planet, which means we're also the first to face a choice: exploit the silence or protect it. There's a parallel here to the early conservation movement, when humanity realized wilderness wasn't infinite and needed safeguarding. The difference is that space silence isn't just beautiful, it's foundational to discovery. Future breakthroughs about dark matter, quantum gravity, or the origins of life might hinge on signals we haven't even thought to listen for yet. By filling the quiet today, we could blind tomorrow's scientists to revelations we can't yet imagine. Some argue progress demands sacrifice, that the benefits of global connectivity and space exploration outweigh the cost to radio astronomy. But what if we're not facing a binary choice? Innovative solutions are already emerging. New satellites can be designed with quiet hours, powering down transmissions during critical observations. Governments could expand protections for radio quiet zones, treating them like the intellectual nature reserves they are. Even everyday technology can help. Japan's Halka satellite used a solar sail to maintain orbit without noisy thrusters, proving low-impact spaceflight is possible. The deeper question is one of legacy. When future civilizations look back at this era, will they see a species that shouted mindlessly into the dark, or one that learned to listen as much as it spoke? The universe's quiet isn't empty. It's a shared resource as vital to understanding our place in the cosmos as clean air is to breathing. Preserving it isn't about stifling exploration. It's about ensuring the conversation never ends. Time behaves differently in the quietest corners of the cosmos, not because those places are special, but precisely because they're so empty. Picture two identical atomic clocks, one placed on Earth's surface, ticking steadily under the weight of our planet's gravity, and another drifting in the vast emptiness between galaxies, where space-time curves gently into near-nothingness. According to Einstein's general relativity, the clock in deep space would gradually pull ahead, its ticks coming microseconds faster over years, not because it's malfunctioning, but because time itself flows faster where gravity's grip is weakest. This isn't science fiction, it's a measurable effect called gravitational time dilation, and the quieter the region of space, the clearer the signal becomes. The reason lies in spacetime's flexibility. Massive objects like stars and planets dent the fabric of reality like a bowling ball on a trampoline, slowing time in their vicinity. But in cosmic voids, those sprawling deserts where galaxies are few and dark matter spreads thin, spacetime relaxes into something closer to its natural state. Here, far from the gravitational traffic jams of clustered matter, time runs with fewer obstacles, like water flowing faster down an unclogged pipe. The difference is tiny, a few seconds over millions of years, but modern atomic clocks aboard satellites like GPS systems already account for these relativistic nudges. Without adjusting for Earth's gravity versus orbital altitudes, your phone's map app would misplace you by kilometers within hours. What's astonishing is how these silent regions become laboratories for testing relativity's limits. In 2021, astronomers used the Hubble Space Telescope to observe a quasar whose light passed through one of the universe's largest voids. By measuring how the light's wavelength stretched during its journey, they could essentially weigh the void's gravitational pull, or rather, its lack thereof. The results matched Einstein's predictions with eerie precision, proving that even in near-perfect emptiness, spacetime still plays by his rules, but the real test comes when we push these observations further. Some theories of quantum gravity suggest that on the smallest scales, time might stutter or fracture in ways that defy relativity. To spot those glitches, we need environments so still that even the faintest tremors in time's flow wouldn't be drowned out. Consider pulsars, the universe's most precise timekeepers. These spinning neutron stars beam radio waves with metronomic regularity, some as consistent as atomic clocks over decades. When a pulsar sits in a quiet galactic neighborhood, free from the turbulence of dense gas clouds or companion stars, its rhythm becomes a clean signal for probing time's nuances. The Nanograv project, which monitors dozens of pulsars, recently detected a background hum that might be the collective echo of merging supermassive black holes, a discovery only possible because these cosmic lighthouses operate in relative silence. The deeper implication, time isn't just something we measure, it's something the universe experiences unevenly. A civilization evolving in the heart of a galaxy cluster would perceive time's passage differently than one floating in a void. Their physics, their history, even their philosophy might develop distinct flavors based on their gravitational address. It's a reminder that the cosmos doesn't have a master clock ticking in sync everywhere. Instead, time is a local phenomenon, woven into the fabric of each quiet or crowded corner, whispering its own unique rhythm to those who know how to listen. And that's what makes these silent voids so precious. They're not just empty space, they're reference points, control groups in nature's grand experiment. By studying time where gravity's voice fades to a murmur, we begin to hear the subtler notes in spacetime's symphony. The quieter the cosmos gets, the more clearly we can discern the music. The hush of deep space has always been more than a scientific curiosity, it's a muse. Artists and musicians have long turned to the cosmic void not just for answers, but for inspiration, translating its vast stillness into works that resonate with our deepest emotions. Consider the ambient compositions of Brian Eno, whose album, Apollo, Atmospheres and Soundtracks, captures the eerie tranquility of lunar landscapes through shimmering synthesizers and elongated notes that seem to hang in zero gravity. There are no crashing crescendos here, no frantic rhythms, just the careful arrangement of silence and sound, mirroring the way light drifts through nebulas or particles dance in solar winds. Visual artists wield silence with equal power. Take the abstract paintings of Julie Meritou, whose layered canvases evoke galactic collisions and cosmic voids through intricate, overlapping marks that suggest both chaos and order. Her work doesn't depict space literally. Instead, it channels the emotional weight of emptiness the way a void can feel simultaneously desolate and pregnant with possibility. Similarly, the photography of Thomas Ruff transforms raw astronomical data into hauntingly beautiful prints, where the grainy textures of deep-field telescope images become meditations on scale and solitude. These pieces don't shout, they invite viewers to lean closer, to sit with the quiet until it reveals its secrets. What unites these works is their refusal to treat silence as passive. In the hands of creators, it becomes an active force, a canvas for the imagination. The composer John Cage famously explored this with 433, a piece where the musician sits silently, allowing ambient sounds to become the music. While not explicitly about space, the concept mirrors how astronomers listen to the cosmos by amplifying its faintest signals. Both art and science understand that silence isn't nothingness, it's a frequency waiting to be tuned. This interplay between disciplines reveals something profound. Our attempts to grasp cosmic silence often require metaphor. When physicist Janna Levin describes gravitational waves as the universe's soundtrack, or when poet Tracy K. Smith writes about the silent, silver distance between stars, they're bridging the gap between data and wonder. The quiet between galaxies defies straightforward explanation, so we turn to art to feel its scale, to music to sense its rhythm. Even NASA collaborates with sound designers to sonify black hole vibrations or the electromagnetic hum of planetary auroras, not because these sounds exist naturally in space, but because our brains crave a way to experience the intangible. Perhaps that's why cosmic silence resonates so deeply. It mirrors the quiet spaces within us, the pauses between heartbeats, the stillness before sleep. Artists who channel this void aren't just interpreting science, they're reminding us that exploration isn't only about discovery, it's about connection. When a filmmaker frames the emptiness of space to evoke loneliness, or a sculptor crafts a hollow sphere to suggest the event horizon, they're offering us a way to stand at the edge of the unknown and feel less alone. The universe's quiet isn't cold or indifferent in these works. It's alive with questions, and humanity's creativity is the echo answering back. The universe's quietest regions are not voids of meaning, they are theaters of revelation. Think of them as cosmic libraries where the most profound truths aren't written in blazing stars or swirling galaxies, but in the faintest tremors of space-time, the ghostly fingerprints of particles we can't see, and the whispers of light that has traveled longer than time itself. It's in these silent stretches that we've uncovered dark matter's invisible scaffolding, detected the faint echoes of black holes colliding billions of years ago, and even glimpsed the afterglow of creation itself in the cosmic microwave background. These aren't just discoveries, they're revolutions, each one rewriting the story we tell about the cosmos and our place in it. Consider how much we've learned by listening to the quiet. The Hubble Space Telescope's famous deep field image, captured by staring at an empty patch of sky for days, revealed thousands of galaxies in a space no larger than a grain of sand held at arm's length. That single image transformed our understanding of the universe's scale and history. Or take LIGO gravitational wave detections, ripples in spacetime so subtle they'd gone unnoticed for a century, until we built instruments sensitive enough to hear them. These breakthroughs didn't come from focusing on the cosmos's loudest fireworks, but from tuning into its quietest frequencies. What's even more astonishing is how much remains hidden in the hush. The same voids that helped us discover dark energy might also hold clues about the multiverse, with cold spots in the cosmic microwave background possibly being scars from collisions with other universes. The quantum fluctuations humming in empty space could reveal the missing link between gravity and quantum mechanics, and the silent, icy oceans beneath the surfaces of moons like Europa might harbor life that thrives in darkness, rewriting our definition of what it means to be alive. The quieter the corner of the cosmos, it seems, the bigger the questions it dares us to ask. This isn't just science, it's a profound shift in perspective. For centuries, humanity equated emptiness with insignificance, assuming the voids between stars were mere backdrops to the celestial drama. Now we know better. The quiet isn't passive, it's dynamic, a canvas where the universe's most fundamental processes play out unseen. It's where dark energy stretches the fabric of reality, where quantum particles flicker in and out of existence, and where the raw ingredients of galaxies slowly gather. To overlook these regions would be like ignoring the white space in a poem. The silence isn't just punctuation, it's part of the meaning. So the next time you gaze at the night sky, let your eyes linger on the dark patches between the stars. That's where the real magic happens. The loudest answers aren't always the brightest, they're the ones we have to lean in to hear, the whispers that change everything when we finally listen. What do you think the universe's quietest corners will reveal next? Share your thoughts below. And if you've enjoyed this journey through the cosmos's hidden symphony, don't forget to subscribe for more explorations into the mysteries that shape our understanding of existence. The universe is always speaking, we just have to learn how to tune in.